All right, welcome back to Algebra 1. We are in section 7.6, growth and decay, the last section in chapter 7. We just talked about exponential functions in 7.5 and how to graph them. And now we're going to talk about solving problems using exponential growth and decay, so using it to solve different word problems. We got three equations here. We got one for exponential growth, one for exponential decay, and then one for compound interest. And so we'll do a problem for each, and then that should be it. All right, first let's take a look at this equation for exponential growth. Y equals a times 1 plus r to the t. So a lot of stuff going on. Let's make sure we know what everything is. So first, your y value, that's the final amount. That's the last thing. That's a lot of times that's the answer you're going to get is your y after plugging all this stuff in. Your a value here is your initial amount. That's what you started with before anything happened, any growth or decay or interest, whatever. In this case, it's exponential growth. Your r value, that's the rate of change, and that's written as a decimal. So that's going to be your percentage in the problem, and we have to change that to a decimal. That's probably going to be the trickiest part, is making sure we do that, just making sure we change it to a decimal, and therefore we can solve these problems. And then t, the little exponent up here, t, is time, and usually it's in years. Okay? So the first problem here, population in 2008. The town of Flat Creek had a population of about 280,000 and a growth rate of 0.85% per year. So the first one says just to write an equation representing the population of Flat Creek since 2008. And then the second one, we're going to actually solve a problem by putting a number in for the time. So the first one, we take a look, what do we have? Okay, we got the year, and we have a population of about 280,000. So this here, that's going to be your initial amount. So that's going to be your a value. Okay. And what other numbers are they given to us? Well, they give us this growth rate of 0.85%. So that's going to be our rate. All right. That's our r. But remember, we have to write that as a decimal. So how do we do that? At 0.85%, remember, would be we have to move it 2 spaces to the left to make it a decimal. So it's 0.85%. So we had to move this thing 2 spots to the left, which would put another 0 in there. So it'd actually be 0.0085. Remember that as we move along. That's all we have. Remember, we don't have a t here. And the reason we don't have a t is because we're actually just writing the equation. We're going to leave it as a variable. And then in part B, we're going to actually put a value in for t to get our y value. So y and t will stay variables here in our equation. So let's just write what we know, what we have. We have a y. That's our answer that we were going to get from the equation. We have an a value over here of 280,000 times 1 plus r. So it's 1 plus 0.0085. And then to the t in time, which we don't have a time, so we're just going to keep it like that with the t there. That's it. That's your equation. Okay, so that's the answer to that one. Just plugging numbers in from the problem. Okay. Part B says, according to your equation, what will be the population of Flat Creek in the year 2018? So now we're actually going to put in something for t and solve it. Okay, so we're going to start with the equation. We're going to start with that equation of y equals 280,000 times 1 plus 0.0085 to the t. Now we know something has to go there, but what goes there? Okay, so something we need a value up here for our time. But what goes there? Would it be 2018? No, not necessarily. What we're looking at is, where did it start? When did we start? We started this study with the equation in 2008, and now we're in 2018. So if we take 2018, subtract 2008, we get 10 years, and that would be what we're looking at putting in there, 10 for the exponent. So now we've got this crazy equation. Well, our only rule says we have to do Pemdas. We have to use order of operations. So way back in the day, we did Pemdas, right? So parentheses first. So we have to do this parenthesis first. Then we deal with exponents, then multiplication, division, addition, subtraction, stuff like that. Okay, so when we go through this, remember the first thing we're going to do then is take care of this parenthesis and add this up. So you would actually have 280,000 times 1.0085 to the 10th power. Okay? So we add those up. We have to take care of the parentheses first. And now we can use order of operations and say, next is the exponent, so 1.0085 to the 10th power. So this is why you're going to need your calculators to plug that in, 1.0085 to the 10th power. And then we can multiply it by the $280,000. So punch it in the calculator, 1.0085 to the 10th power. Then we can multiply that by 280,000, and we end up getting, you can check my math, but it's 304,731. Now, you're going to get a decimal there, right? But we're talking about population. We're talking about people. So can you have a decimal of a person? Not necessarily, so I rounded it to 731 there. Okay? So that's our example of exponential growth. All right, let's take a look at exponential decay. So on this one, very, very similar. What do you notice that's different? The only thing that's different here is instead of 1 plus r, it's 1 minus r. 1 minus r. It's a difference now. And you think about the minus because of its decay. Okay? So that's what we're looking at there. So what are these mean? So the y is still the same thing. Y is your final amount. That's what the answer you're going to get. A is still the initial amount, the starting point. R is still your rate of change, that's as a decimal. And your T is still your time in years. So nothing else changed. The only thing that changed instead of 1 plus R, it's 1 minus R. So let's take a look at this problem, charity problem. During an economic recession, a charitable organization found that its donations dropped by 1.1% per year. And before the recession, its donations were 390,000. So write an equation to represent the charity's donations since the beginning of the recession. And then B, we're going to actually plug something in. So again, we don't know what we have, but all we know is that this value here, the 390,000, that's going to represent our A, because that's the donations before the recession. Okay, so that's our starting point, A. And we also have this here, this 1.1%, that's our rate. So that's going to represent our R, which then should be, again, we have to change this, move this decimal place 2 places to the left. So 1, 2, gives us a 0.011 for our rate. Okay? And that's all we have. Again, we don't have a T, because T is, again, going to be listed as a variable here. So when we go through this one, we have y equals 390,000 times 1 minus 0.001 to the t power. We don't have a value for t, so we're going to leave it like that. Again, how do we know it's 1 minus? Well, we got to look for certain things in the problem. Here it says donations dropped. So the word dropped, or if something's falling, or something's getting less, then we're thinking decay. Okay? So that would be an indication that we're going to use 1 minus r instead of 1 plus r. So look for those key words in the problem. Now we're going to punch in something for t and see if we can get an answer. All right, so estimate the amount of donations for 5 years after the start of the recession. So that was pretty easy. Gives us right here that t is equal to 5. So that's pretty simple. Now we have to go y equals 390,000 times 1 minus 0.001 to the 5th power. Okay? And again, using order of operations, that's going to be the key. Make sure you do that parentheses first. So 1 minus 0.001. So we're going to have like a 0.999 something in there. Okay? Then take it to the 5th power. Then multiply it by 390,000 because we have to use Pemdas. And you should end up, we're talking money here, you should end up with about 369,016.74. Here I went to 2 decimal places because we're talking money, so we go to cents. And there's an example of exponential decay. Again, look for keywords like dropped or falling or something like that to make sure that we have our exponential decay in there. All right, one more problem. This one is the equation for compound interest. So there's a lot of stuff going on in this problem, a little bit different than what we're working with. Okay, first off, our A value now, that's the current amount. Okay, so that's the amount. It's a compound interest, so it's going on over and over. When do we use compound interest? We use it when we talk about a loan or putting money in the bank for a savings account or saving up for college or a car loan or a house loan or something like that where the money is going to change over time. So this would be the amount that we currently have after a certain amount of time. Your P, that's your starting amount. That's your principal. Okay, so that's kind of similar to the other two equations. Now we have this 1 plus R over N. And so we know that the R is the number of times, we know our R is our rate, And our N, I put it at the bottom here, it's the number of times compounded each year. So we know R is our rate, and I put that up top here for you to see because it's on top of the equation. And then I put the N down here in the bottom. That's the number of times compounded each year. Okay, so we think about it, it could be more than once per year. All right? So down here I have annually is once a year. Okay? So that would be our N value if it says annually. What would semi-annually be? Well, it would be twice a year. Quarterly, 4 quarters. Okay, right? And then you guys can kind of fill in the rest of these if you compounded it monthly, weekly, or daily. Finally, up top, we have an N times a T. We know time is in years, and you still have the N there. The N is the same thing. So that N is not only in the bottom of this, the parenthesis here, of the denominator, but it's also part of the exponent there, and it appears twice. Okay, so it's a little bit different of a formula, a little bit more complicated. So let's take a look here. When Paige was born, her grandparents invested $1,000 in a fixed rate savings account at a rate of 7% compounded annually. Paige will receive the money when she turns 18 to help with her college expenses. What amount of money will Paige receive from the investment? Okay, so again, looking at this problem here, we have a bunch of different numbers. We look at it, we've got a rate, we know that, we see the 7%. The percent should jump out at us that that's the rate, so that's R. And I'm going to move the decimal 2 places to the left, so it's 0.07. I got to write it as a decimal. The next thing I notice is that my 1,000 here is my principal. That's my initial amount, so that's going to be my P. And then I have compounded annually. When I read through the problem, it's compounded annually. So what does that mean? Annually means once a year. So that would be our N value that we're going once a year, according to our table above, right? Annually. Paige will receive the money when she turns 18. So 18, that's time in years, because it was when she was born to when she's 18. So 18 is our time. 18 would be our time. So we have a lot of stuff. What don't we have? We don't have an A. Okay, we don't have an A. So we're going to look at that. So here we go. Our equation would be A equals 1,000 is our P value. That's the principal. Now in parentheses, we've got 1 plus R over N. Well, R is 0.07 over N, and happen to be 1 because we're compounding it annually. Here's where you have to know how many times they're compounding the interest. If it was semi-annually, you'd plug a 2 in here. If it was quarterly, 4, and so on and so forth. In this case, it's annually, so it's 1. So 0.07 over 1. And then our time again, our exponent is N times T. Well, we know N is 1, and we know our T is 18, so it's 1 times 18. So again, if it's compounded more often, you're going to have a multiplication problem here. So we continue on. We know that this then is 1,000. We're going to have 1 plus 0.07 over 1, and I could do that multiplication problem of 18. Now, again, Pemdas is the key. Make sure we do order of operations correctly. and you guys can calculate this out. But we have to do the parenthesis first. So we're going to go 0.07 divided by 1. Have to do that first in the parenthesis because you still have to do Pemdas, order of operations, within the parenthesis. So division here comes before this multiplication, or excuse me, before this addition. So I'm going to divide 0.07 by 1. You're going to get 0.07. Then I can add it to 1, so I'd get 1.07. And then I'm going to put that to the 18th power. So you need your calculator. There's a little caret button that you can plug in this number 1.07, and then hit the caret button up to 18, and that'll give you the 18th power. Then multiply it by 1,000. So a lot of steps, but as long as you use order of operations, you should be okay. And then after adding this up and doing the multiplication, doing order of operations correctly, you should get 3,379.33, or $3,379.33. So that $1,000 that was put in initially 18 years ago turned into $3,379.33. Okay, so that's compound interest. Now there's a lot to it. Just try to keep them straight. Lesson summary. I want you to summarize in your own words what this lesson was about. You tell me what the lesson was about. And we got our practice problem here. Population. Population of Johnson City in 2005 was 25,000. Since then, the population has grown at an average rate of 3.2% each year. So that's just the problem right there. And then down here it says write an equation to represent the population of Johnson City since 2005. All we're looking for is an equation. We're not going to have to solve it because we don't know what t is. We don't know what the time is. So t is going to stay as a variable. So you're going to have a variable of y. You're going to have a variable of t. The big thing is what equation do you use? Do you use compound interest? No, there's nothing that says anything about compounding that interest at any time throughout the year. It's just population growth or decay. So in this case, look at the word grown. That should give you an idea of what equation to use. Okay? So work on that. Bring your questions. We'll work on this. I know it's a lot to throw at you, but as long as you can plug numbers into equations and keep the equations straight, you'll be fine. Okay? That is it for chapter section 7.6. That is it for chapter 7.